Hey students, in the last video we talked about tooling forces and the effect that they have on our fixture, and we saw that there's a wide range of tooling forces that can be in effect. So in this video what we're going to talk about is how do we go calculate our own tooling forces so we know for the process that we're going to be doing what we should choose. All right, so let's go get into that. The first thing that we'll need to do is we need to calculate our feeds and our speeds. And so there are lots of places that you can go to get that. The manufacturer of your tool may have information on what they'd like you to use. One that I really like that has great information and great usability is the Helical Tools Machining Advisor Pro. You do have to sign up for a free account with them to get this. You can opt out of all their emails if you want to, and it just works really, really well. The only downside to this is that they conveniently have the very first thing that you have to choose about your tool is the Helical Tools tool number. So you will have to go into their database and find a tool that is similar to the one that you want to analyze if you're trying to use a tool from a different manufacturer. However, the Helical tools are outstanding tools, so if you have the chance to buy them, that would be good too. Then after you've done that, we need to go to one of the other cutting force calculators, and those typically are not the same as the cutting feeds and speeds calculators. And so you can get those. Kinemetal Tools has a really good one, though it is not their first priority to keep this running. So over the 6 years that I've taught this class, I would say that this calculator has been running for 4 of those years, and 2 of those years it was broken for the entire quarter and never worked. So you should always have another cutting force calculator in your back pocket. The ISCAR website has information. If you look around, you can find other cutting tool calculators. And then remember, overall, you have to make sure to add a factor of safety for dull tools or hard spots in the material, or somebody cranking up the feed rate override while they're cutting, or just any of those things that can happen, any variation in the process. And so we need to make sure that we add a factor of safety to the force that we calculate so that we don't throw parts out of the machine. Okay, so let's get right after it. First thing that we're going to do is we're going to go to the Helical website. And you can see on the Helical website, helicaltool.com, here is the Machining Advisor Pro. So I'm going to click on that, and in a minute it'll come up, and I tell it that I want to log in. It already has my information in it, and so it let me log in. Okay, I'm going to make me disappear for a minute, hopefully. There we go. That worked out very well. Okay, so we need to start out with a tool number. Well, I did a little bit of work before, and I wanted to use a 1-inch diameter tool, and so I picked one that it has a 2-inch length of cut. Yeah, and so it's tool number 1750. Actually, well, yeah. It's just tool number 1750, so 01750, and this has information. It is an aluminum cutting tool, and when I hit OK, it pre-populates some information in there about the type of tool, 35-degree helix. It is a 1-inch diameter tool with a 2-inch length of cut, 3 flutes. I like 3 flute tools. They're a good middle ground between 2 flutes and 4 flutes, not surprisingly. Oh wait, I became huge again. Wow. Okay, now I am gone again. Sorry about that. So then I have to choose the material. So I'm going to use wrought aluminum. So we often cut aluminum 6061, which is aircraft grade aluminum. So I'm going to choose that. The condition is the heat condition of it. So you can do an aging post production age and temper, and so this is a T6 temper on the material. That is the most common that we use. Okay, we're going to do general milling, and what are we going to do? Well, we could do any of these different milling processes, and so you would choose the one that matters to what you're doing. For this case, I'm going to choose the worst case and say, well, full slotting is the worst case option that I could have. That's the highest forces, and I may end up with some full slotting, so I'm going to calculate that to begin with. I go over here, this is the type of holder that we have, and so CV40 means a CAT 40 taper, and so that is the most common kind of tool holder, and it's the kind that we have in the lab. The holder beyond that is an ER collet. This is just something that you would have to know or guess or try to figure out, but those collets that you use, the collet holders, are all ER32s, and so it's an ER type collet. The reason that they need to know that is because the different types of holders do better and worse jobs at holding onto the tool at really high speeds, and they have different amounts of deflection in them. Okay, max RPM on that machine is 15,000. We're going to do this on the 5-axis machine. Oops. Ah, yes, that made me come back. Sorry. And I hit the I typed it in on the keypad, so flashing all over the place. Sorry about that. And then my max inches per minute on that machine, we're going to say 800 is about our max inches per minute that we can run on the machine. We can choose here whether our work holding is good or bad, whether it holds it loosely or it's pretty rigid. We're just going to leave it in the middle for right now. We can come down to this, and this is the part of this calculator that I really like. So you can see that it came out and it started with the stick out being 275%. When it has it in percent, that is percent of the tool diameter. Here is the number in inches. I wish it listed inches, but it does not. Anyway, so 275% of 1 inch, so that's 2.75 inches, is the amount that sticks out of the tool holder. The radial depth, or the width of cut, is 100%, which is 1 inch, and that makes sense because this is slotting, so it's going to cut across the full width of the part, and then the depth could be all kinds of different things. We're going to leave it at 1 inch just because that's what it has. But let me show you what this tool calculator does. So if I, instead of slotting them and cutting along the edge of the part, actually it won't let me adjust that because it's slotting, but I can take this and I can change the axial depth of cut. And when I do that, it is automatically updating all of these speeds and feeds over here. So that's really nice that it does that. Oops. And so that's pretty cool. All right, so things that we need to write down from this. Our surface footage, our surface speed is 2,100 surface feet per minute. So 2,100. And our feed per tooth is 0.0055, so 5.5 thousandths of a feed per tooth. That means every time it gets to the next tooth cutting, the tool has moved forward by 5.5 thousandths of an inch. That will be the thickest part of the chip that it takes, and then it will get thinner from there. Feed per minute is 132 inches per minute. And the rotation speed of the end mill is 8,000 RPM, and so we can use that just to check it. So then I go over to Kinemetal. So here's kinemetal.com. I go to resources and then down to engineering calculators, and we could choose in milling, or because I'm doing slotting in particular, I can choose the slotting calculator, but both of these can calculate this particular condition. So I hit slotting calculators, and what I want to calculate is the force, torque, and power. So I will click on that, and it's going to ask me some questions. So I can choose my units, and it says what is the hardness of the material. So I did a quick search, and for aluminum, actually it also listed it on the last page for what they were assuming, but is 56, and that is Rockwell B. Oh, drat, see, I used the wrong keyboard again. Sorry about that. So 56 Rockwell B, I can press calculate the hardness, and it comes up with 101 Brinell. And so then the ultimate strength is 50,500 psi. Okay, effective cutting diameter is 1 inch. Number of inserts or flutes is 3. The cutting speed that we just got was 2100. The radial depth of cut is 1 inch. The width of the axial depth of cut, this is bad. The depths are kind of backwards from depths and widths from the way you think about them. So you have to pay attention to the radial and the axial. But anyway, they're both 1 inch in this case. The feed per tooth is 0.0055. And then we come down here and something that we don't know the answer to, radial engagement factor. So if you hover over the question mark, then up here on this top line it says aluminum alloys, and we need to find the ratio of our width to the depth of the cut. And in fact ours is a width to depth ratio of 1, so our radial engagement factor, we use a value of 1.1. And then machine efficiency factor, the reason that it needs to know the machine efficiency is because it's going to calculate the horsepower that we need to be able to run this part. And so we look at these different options, and this machine is a direct belt drive. So that's the most efficient at getting horsepower, motor horsepower delivered to the spindle. All of the rest of these have losses in the drive system. So 0.9 is what we get to use here, and we hit calculate and then scroll down to see what it said. And it says, okay, it's going to run at 8,000 RPM. That's good. That's what the other calculator said as well, and 132 inches per minute. So this is all calculating. It's matching up to the previous calculator, so that says that I entered the correct numbers. We come down here and we see that the tangential cutting force is almost 600 pounds. Now this one says inch pounds, but that doesn't make sense for a force. They just made a mistake on their units. It is 600 pounds, and the torque at the cutter is 300 foot-pounds. 300 inch-pounds or 24 foot-pounds. There we go. And then we can also see down here, this is the machine power, and notice that the machine power at the motor is 42.11 horsepower. So this would immediately be a tip-off that we cannot run this on the machine that I was going to run it on under these conditions. So we would have to go back and calculate a shallower axial depth of cut, because that machine is only 40 horsepower, and it is only 40 horsepower at one specific RPM setting, and everywhere else it is lower horsepower if you look at the horsepower curve. But anyway, so we got some numbers from this. 600 pounds, 300 inch-pounds of torque, and got a horsepower number. So now we're ready to figure out what to do with this. All right, so let's see what we should do with this. We'll do that in the next video. See you there.